Between them came up with the idea that all these curves should be part of the same notional big sphere. So if you look at this, these are all spherical shapes, whereas the initial drawing was more random. And this gives you a system of constructing ribs that all are on the same arc, and each rib is long, but it's always on this dimension, which is about, I think, 80 meters in diameter, or maybe 80 meters in radius. So this produces something that's very, very regular. Now, I guess an engineer would say the regularity gives you a geometry of construction, but it also gives you a kind of feeling that there's a rule beneath the appearance of the thing. So it actually feels aesthetically pleasing. So the system of manufacture, the pleasing impact it has on the eye, are kind of connected together. And funny enough, outside the Sydney Opera House, they put up this bronze memorial, or not memorial, memento of how the system works. You can see these are the shells as if they've been taken out of the pieces of the orange. It's quite a brilliant solution to something that was very irregular and almost arbitrary, you know. So people gather round and, you know, they go and look at the opera house, and then they gather round the little bronze statue. A little bit more about the opera house. I'll try and hurry up a bit. This is what Utzon said when he had this idea. He saw this as a radical breakthrough, and you could see that the whole shape of the shells, by cutting each of them out of the same sphere, so that the ribs followed the same curve. That meant you had a way of prefabricating the whole roof structure. And there it is. How many of you have been to Sydney? Have you seen this building? Did you like it? It's a stunning building. I mean, it's quite extraordinary. Someone described it as copulating terrapins.
Some people with a dirty mind, like science engineers, don't think like this.
And here's the cross-section of the rib. So you're building a series of cross-sections. So you're building this rib so it can extend and extend, but it's always on the same curve. And then you put each of the arch-shaped enclosures together from the same set of components. So it's rather like a fancy system of Lego in a way. So Arup is the person that would have worked out the detail of this. This is post-tensioned. You know what post-tensioning is? You actually have pieces that are like that, one on top of the other, and you run wires through them and you tighten them up. Like pushing books together. So that's what all these things are. That's how the opera house is built.
You realise that David is an architect, and he's really excited about that stuff.
Yeah, I am. But my respect for engineers is really encapsulated in that story, because I guess Utzon would have got to some of that, the spherical idea himself, but working out the details so that the thing doesn't fall down and it can be built is just another level of difficulty, okay? And people use the expression, God is in the details. You can do everything right, you can have a really good building or artifact or piece of technology or automobile or whatever it is, and some little thing will go wrong that could turn into a complete disaster. So God is in the details. Even if you look at quite ordinary artifacts, this is a shot of a Coca-Cola can. I'm always impressed by the workmanship, or the workmanship of certainty, if you like. This thing is pressed out in its millions, but it's actually got a kind of beauty in terms of its material and the way it's responding to the problem that it's solving. So even in very, very simple artifacts you can see that. If you look at more complex artifacts like this racing car, you know that behind the artifact is just an enormous amount of effort that's gone into the engineering and the drawings and the assembly, putting it all together. You also know there's a lot of craft that's gone into building the thing in the workshop. And sometimes they just work off a few dimensions and a jig or a former to do the various components. This brings me to a fairly important series of points, which is about the process that you're involved in as engineers. This is something from management, okay? People talk about the development funnel. Rainer and I are professionally very, very interested in new product development. New product development, roughly speaking, is an ice cream cone turned on its side, okay? You've got the fuzzy front end, and you've got something that comes out the back. This is from a management book, but I think this is quite a good conceptualization to have in your head. Engineers are very, very good at this. You know, right in the downstream end of the funnel. They're good at narrow problems, they're good at delivering results. They are quite uncomfortable at the front end because there are too many uncertainties, too many unknowns, the brief is not tight enough, and professionally they've been taught to solve tight problems. They don't really like dealing with what you might call fuzzy problems. So here's a way of expressing it. There are loose problems or wicked problems at the beginning that are converted into tight problems and produce tight solutions.
Yeah, it was on a timer. Huh?
That's okay, speed up, David.
Mm. And whatever we do in engineering design is generally at the tight end, the detailed design.
Yeah.
Designing a pressure vessel. We know already what the problem is. We have got the idea in principle, you know what it's all about. And what we are doing is we are dotting the I's, and crossing the T's.
Yeah. I think if you look down the funnel, if you imagine turning the funnel sideways, you could say, well, the process of engineering is organizing all these constraints so they give you a really tight problem to work on. And I don't think there's much wrong with conceptualizing the process like that. But it doesn't mean to say that someone else is working on a solution over here which has got a different set of parameters and constraints. And these constraints are not fixed. That's the other thing. So engineers are convergent, they're good at detail, they love being in the lab, they love to have problems that, you know, can I just get on with it, can you leave me alone, don't bother me with all the fuzzy stuff. Now, one level that's a virtue, because you need those people to solve, but at another level it's a handicap. Because if they want to join in the earlier discussions at the front end of the funnel and maybe run businesses themselves, they are educationally and maybe temperamentally less capable of doing that. Okay? So that's something you have to think about in your own makeup and your own skills. You know? What happens if you are plunged into a situation where the boundaries are fuzzy, where things are dynamic, where there's lots of other people who are not engineers putting demands on you?
And this is something which you have encountered, or which you do encounter in your work with Engineers Without Borders, quite clearly. You're getting out of the boundaries that you're familiar with. You're getting into a totally different environment.
Yeah. Rainer has done a lot of work with small businesses in Auckland. This is one of our kind of rules coming out of Innovation NZ. Competitiveness is founded on high levels of technological know-how. How can you actually be competitive in these small businesses if you aren't on top of really good technical skills? So that's where the strength of the engineers comes into play. But the weaknesses, to reiterate them, is that they dislike uncertainty. They're not necessarily very good in teams. You can make your own judgments about yourself. And they're not very good with other groups of people.